Here we're going to look at the difference between a conservative and a non-conservative force. While this distinction is going to look fairly abstract, it's really related to the conservation of energy. And we're going to distinguish between mechanical energy, which technically is the only thing we're going to worry about being conserved, and total energy, which will include what could be called internal energy, which includes things like thermal energy, which is often called heat, the random kinetic energy of the motion of molecules, as well as chemical energy in the bonds between atoms and molecules. We're only going to worry about mechanical energy, which will be a combination of kinetic energy, which involves motion of the center of mass of an object, as opposed to the internal random thermal energy, and potential energy, which will be associated with gravity and with springs that follow Hooke's law. Combination of kinetic and potential energy we're going to call mechanical energy, and we say energy is conserved. That's what we really mean. And we'll see why there's a distinction between forces that are involved in potential energy, like gravity and Hooke's law springs, versus friction, which generates heat. Now, what we really want to be able to do is say that the energy in a system is purely a function of the state of the system. Remember, a system is a collection of objects that interact. The interactions we want to make to be conservative forces, so that we will have a function that will map the states of those systems, which will include the velocities and the positions of all of the objects, into a unique value for how much energy is in the system. And that energy depends only on the state of the system, not on how the system got into that state. It doesn't depend on the history of the system, only its current state, which is to say, where are the objects and how fast are they moving? So we have to have a way to map the state of a system into a value for energy. Now, kinetic energy is straightforward. That's just 1/2 mv squared. However, potential energy is the thing that we have to worry about. So a function in mathematics is defined so that we have a collection of points right here, which we call the domain, and we have another set of points over here, which we call the range, and a function is a one-to-one mapping of points in the domain to points in the range. The key thing about a function is that each point in the domain is mapped to one and only one point in the range. Notice right here I have two different points, D and E, that are both mapped to the same point in the range, Y. That's perfectly fine. What I can't have is the point D mapped to Y as well as X. D can be mapped to one and only one point, which is to say each position of an object in a system must be mapped to one and only one value of potential energy. So I can't say if an object is right here, it could have 1 joule or it could have 2 joules of potential energy. It can only have 1 joule. However, a point over here at A could also have 1 joule of potential energy. That's perfectly fine. But each point in the domain must have one and only one point in the range. And what we need to do is find a mathematical tool that allows us to map where objects are to how much potential energy they have. If we can do that, then we say the force is conservative, and we can define a potential energy function, which is a function only of the state of the system. That energy will be conserved. If we can't do that, if this point right here, an object is sitting right here, and we can't give a unique value to how much energy it has, then the force involved is non-conservative, and we can't say that energy is conserved. So what we're going to do essentially here is replace the idea of a force with the idea of potential energy. Now, conservative forces. What we're going to do is say here, these are 2 points in space, O and P. We're going to let O be our reference point, and we're going to define the potential energy right here to be 0. That'll be our reference point, the origin of our coordinate system. And we're going to find, can we calculate how much potential energy is at point P? Our idea is we're going to use the work done in going from O to P to define the potential energy. If we go from O to P as a straight line, we can calculate how much work is done. However, that's not the only way to get to point P. We could take this second path right here. That would also go from O to P. We could calculate how much work is involved in going via that path. We also could take some crazy looping path to go from O to P and calculate how much work is done as we go from O to P. So this integral that we could form from starting point to the ending point of f dot dx, in a sense, we have to be careful because we could take multiple different paths in going from O to P and calculate the change in potential energy, which would be the difference in potential energy at P minus the difference in potential energy at O, which we've defined to be 0. And that would give us the potential energy at this second point. If the value of this integration depends on the path taken, then that's a non-conservative force. If it does not depend on the path taken, it is what is called path independent, then it is a conservative force. Turns out gravity is one such example. Because gravity, particularly as we're going to consider it in a uniform gravitational field where the gravitational force is always vertically down, the only displacement that matters is the vertical height. How much higher is P than O? That's all that gravity depends on. All of the horizontal motion, the force and the displacement will be at right angles to each other, and the dot product will be 0. So if I want to go from O to P, I can break any one of these paths into a series of small horizontal motions and small vertical motions. The vertical motions will contribute to the work. The horizontal will not. But the vertical motion will always be the same if I'm starting at O and ending at P. The vertical displacement will always be the same. Therefore, gravity is an example of a force where the work done from O to P does not depend on how you go there. Therefore, gravity is a conservative force, and I can give a unique value for the gravitational potential energy at P once I have defined the value at this reference point. Now, let's take another example of a non-conservative force. What this says is that the work done does depend on the length of the path. Friction is one such example, because the amount of heat generated depends on the length of the path taken. The shorter the path, the less work is required to push an object from here to here. It takes a lot more work to push an object down some round, crazy path of longer length going from O to P. And that's because friction is always in the opposite direction of the motion. The applied force required to go from O to P always opposes the friction. The dot product is always positive and will always add up all along the length of this path. And because this path is longer, there'll be more sums to add up, and therefore more work will be done. The amount of heat generated as I go from O to P will depend on how did I get there. I cannot define a unique amount of thermal energy at point P. It depends on the history. How did the object get from O to P? If it depends on the length of the path, that's a non-conservative force. I cannot define, once I see an object sitting right here, I can't say, aha, that must have 3 joules of heat in it. It depends on how it got there. Therefore, friction is a non-conservative force. I cannot define a potential energy for it. Therefore, it is not considered conserved. In summary, therefore, a conservative force will lead to the conservation of mechanical energy. The integration for work is independent of the path taken between some starting or reference point and some ending point. The potential energy at some point is the potential energy at the reference point, which we're going to define to be 0, plus the work done in getting to the second point. Mechanical energy is the sum of kinetic and potential. That is now a function purely of the state of the system, and we'll say that is what we mean by being conserved. Non-conservative forces, I cannot make that path independence. The work does depend on the path. I cannot make a mapping from points in space to values of energy. Therefore, that we're going to call a non-conservative force. This is a bit abstract, but the key thing is whether or not a force can be replaced by a function for which each state of the system can be given a unique value for how much energy the system has.